Second order linear homogeneous ODE. In fact, these are constant coefficients. A, B, C are constants. Homogeneous means the right hand side is 0. Obviously, second derivative, so second order. Linear means y, y prime, y double prime, and the coefficients are just constants or functions of independent variable. So the independent variable is t, because y is a function of t. And to solve, we just assume y be some exponential function. Okay, let y be a solution. Now we want to determine the value of r. We want to plug this back here. Y, y prime, y double prime. Okay, then we need to find y prime and y double prime. This is y, so find y prime, find the derivative, and second derivative. Now plug these back here. So a y double prime is here, plus b y prime is here, plus c y equals 0. From these three terms, we can factor exponential function out here, and that leaves ar squared plus br plus c equals 0. So we got a product of two things 0. That means one of them, at least one of them, should be 0. This exponential factor is never 0. That means this is 0. And in fact, the nature of the solution, okay, is determined by this equation. I mean, the solutions are characterized by this quadratic polynomial in R, where R is unknown, in fact. Okay, so, and this is called the characteristic equation of 1. And when we solve this equation 2, okay, which is a quadratic polynomial equation or quadratic equation, so we have three cases. The roots could be real and distinct. Roots are complex conjugates, and roots are equal. So solving 2, we get three cases. Okay, so case 1, and this happens when we find the discriminant b squared minus 4ac. Okay, that is positive. In this case, roots are real and distinct. Okay, in this case, let's say the roots are r is r1, one value, and r is r2. In that case, the solutions go up. Look at here. All we have to do is simply plug in r1 and r2 for this r. So we get e raised to r1t is one solution, e raised to r2t another solution. And the general solution is, so in this case, 2. So e raised to r1t and e raised to r2t are solutions. In fact, they form a fundamental set of solutions because they are linearly independent. These are solutions, and the general solution would be then y equals c1 or a, uppercase a, same thing, e r1t plus c2 e r2t. If the initial conditions are given, we need two initial conditions. In that case, we can determine the unique solution. I mean, we can determine C1 and C2. It's case 1. Case 2, if this discriminant is negative, then we get the roots complex conjugates. So in this case, the roots of 2, I mean the values of r from 2, roots are complex conjugates. So let's say r1, r2 are just lambda plus minus mu I. r1 is plus and r2 is minus. The roots always, complex roots always come in pairs. So in this case, the solutions are the general solution y equals this lambda, so e raised to lambda t, we can factor that out. In fact, c1 cosine this mu t plus c2 sine mu t. Okay, this will be the case. Now case 3, if the discriminant is 0, b squared minus 4ac is 0, then we get equal roots case. Let's say r1, r2 both equal, that's r. Then we have one solution is just ERT. So we have only one solution, by the way. We cannot have two solutions. So that's the problem, because it's a second order ODE. That means we must have two solutions, and by the way, they must be linearly independent. When we have one solution, we can multiply by a constant, any number. That will be also a solution. But that is not linearly independent. We want linearly independent solution. So this is one solution, and to find second solution, we multiply the first solution by some variable, some function of t, not a constant, okay? Some function of t, and plug this back into the original ODE and find the value of that constant. So see the textbook if you like to find that constant, and that constant comes out to be t, e raised to rt. So these two are linearly independent solutions of ODE, and we can write down the general solution. General solution yt equals c1 e raised to rt plus c2 t times e raised to rt. Okay, so we already considered case 1 and case 2. So let's do some examples. Using case 3, the question is solve the ODE, and we got 9y double prime plus 6y prime plus y equals 0. To solve this ODE, we find the characteristic equation. I'm using shorthand notation. Characteristic equation: ar squared plus br plus c equals 0. A is 9, so 9r squared plus 6r plus 1 equals 0. And let's solve. We might have to use quadratic formula, but it looks like it can be factored. 3r 1 times 1 1 plus plus. So 3r plus 1 quantity square equals 0. So we get r is negative 1/3, negative 1/3. So negative 1/3, again negative 1/3. Don't have to write twice, but that means we got repeated roots. Okay, r1, r2 both negative 1/3, 1/3. Then the solution is here. One solution is e raised to negative 1/3 t, and second solution is t times the same thing. So we can write down the general solution, which is c1 e raised to rt, which is negative 1/3 t, plus c2. Now second solution will be same thing, but we need to multiply by t. So t times e raised to negative 1/3 t. Okay, let's do another example. In this case, we'll solve the initial value problem, which is 9y double prime minus 12y prime plus 4y equals 0, and we have two initial conditions. Y at 0 is 2, and y prime at 0 equals negative 1. Okay, first let's solve this. Let's find the general solution, and with the help of these initial conditions, we can find the particular solution. Okay, for we find characteristic equation AR square means 9R square plus BR, negative 12R plus C, 4 equals 0. And we can factor this, by the way. 3R, 2 times 2, 4, to get negative, negative. 6R, so 12R. So R is 2/3. So we got repeated roots. That means the general solution is C1 e raised to RT, 2/3 T plus C2. Now we cannot have the same solution, so T times e 2/3 T. Okay, now using these initial conditions we can find the values of C1 and C2. So let me use the first, y at 0 equals 2. So using y at 0 equals 2, so y value is 2 when t is 0. So this y value is 2 when t is 0. So this is C1 times e raised to 0 is just 1. So C1 times 1 is C1 plus C2 times t is 0. Oh, t is 0. So this is 0. So everything is 0, by the way. So we don't need to know. This is just 0. So C1 is 2. Now we can update this solution. So y is in fact C1. We just figured out 2 e 2/3 T plus C2 to be determined, T times e raised to 2/3 T. Now using the second initial condition, which is here, we need to determine the value of C2. But the second initial condition requires us to find derivative. Look at this, y prime, okay, is a prime. That means we need to find the derivative first, then we can apply second initial condition. So this is y. So y prime, let's find the derivative. 2 times 2/3 from general, so 4/3 e raised to 2/3 T plus C2. Oh, we got a product of two functions, so product rule. Derivative of t is 1 exponential function plus t times derivative of exponential, which is 2/3 e raised to 2/3 T. Okay, we don't have to distribute. So using the second initial condition, which was y prime at 0 equals -1, that means y prime is -1 when t is 0. So this y prime is -1 when t is 0 equals 4/3 times e raised to 0, because t is 0, e raised to 0 is 1. So just 4/3 times 1 is 4/3 plus inside t is 0. So this t is 0 means this is 0. Okay, and e raised to 0 is 1, so this is just C2 times 1. Okay, e raised to 0 is 1, so just C2. Okay, move 4/3 over, then we get C2. -1 minus 4/3, that's both negative, so -7/3. Okay, so we have C1 and C2. So the solution is given by here yt, not y prime. Here with C1 2, C2 -7/3. The particular solution, because C1 is 2 e 2/3 T plus C2 is -7/3, so -7/3 T e raised to 2/3 T. Final